for our final video of the course, let's try to recap some of the key concepts and principles we've covered, sort of like our roadmap or our journey through the course. Obviously, it won't cover everything. It's a challenge just to get all of them on board, but I think we got it all on here without squeezing it too much. So remember, we started off just talking about Einstein in context, which meant looking at the scientific background of his time, some of the key scientific discoveries and developments throughout the 1800s, Einstein being born in 1879, of course. Also the technology of the time, because remember his family was very involved in electrotechnology, and of course later on he worked as a clerk at the patent office, and so saw a lot of the things that were going on in terms of, especially things like synchronization of clocks and other things going on in electrical technology of the time. We can't draw a direct connection between those things to some of his work, especially in the special theory of relativity and the relativity of simultaneity and clock synchronization, as we talked about. But it's certainly part of the environment there, and it may have in some way inspired his thinking on some of these matters. So both the science and the technology of the time is important. We talked about 1905, his miracle year, some of his early struggles as well, if you read the Young Einstein article. So we talked about the key papers in the miracle year, with a focus, of course, on the June 1905 paper on the electrodynamics of moving bodies, which is what we know as a special relativity paper. We also noted that what really bothered him were certain theoretical asymmetries in terms of what was going on. We talked about some of the experimental results, especially the Michelson-Morley experiment and stellar aberration. They did not seem to have as big an influence on Einstein's thinking as just some of the, again, as he termed it, the asymmetries involved. We talked about the bar magnet and the coil of wire, and how, depending on which was considered to be moving, physicists had one explanation for one scenario, another explanation for another scenario, and things like that really bothered Einstein, to the point that he described it as, after years of thinking about this, by this time being 26 years old, it was almost a state of psychic tension for him. And then out of that, through some conversations with his friend Michael Besso, you may remember his flash of insight that time was suspect, as he later termed it. So what he then did is he took two key principles that were well established in physics. One, the principle of relativity. So we spent some time talking about Galilean relativity and just the basic principle of motion of objects and how you can convert from one frame of reference to another frame of reference if they're moving at a constant velocity with respect to each other. Talked about that a little bit. And the other principle was what he termed the principle of light constancy, that the movement of a source of light, or really a source of waves, means that it's not going to actually affect the velocity of the waves coming out of that. So we spent some time just talking about how waves work to get some background on that and understand this principle of light constancy. And then also the conflict between them, because the principle of light constancy implied that an ether existed, and it was just assumed that you had to have some sort of medium for, if light was a wave, you had to have some sort of medium through which it traveled, and the idea was that it was this thing called the ether, and so they spent a lot of time creating models of the ether, wondering about how it might work, be put together, and so on and so forth. And the problem with that, though, is that it went against the principle of relativity, because if you had an ether, you could assume the ether was the absolute reference frame. And so you could have absolute motion measured against the ether, or just a state of absolute rest would be the ether, the underlying foundation of the universe, as it were. And so Einstein saw this conflict here, and he said his insight was, actually, they're both true here. And out of those two principles, then, we showed that you get the invariance of the speed of light. That combine those two things together, it's not just that if you have a moving source, the light coming from that moving source has a constant velocity, an invariant velocity, but it's any motion at all. One observer to light, or to another observer moving with respect to light, speed of light will always be the same to all observers. And that came from the combination of these two seemingly incompatible principles. So that was Einstein's key insight that set him off on this path. And then from that, we looked at, okay, what do we get out of that? Well, one key thing was the so-called relativity of simultaneity, that clocks synchronized in one reference frame will not be synchronized in a moving reference frame. We talked about the concept of a lattice of clocks for each reference frame that would be synchronized. And so the relativity of simultaneity, or the relativity of clock synchronization, that was a big news for the time, because the standard assumption was, well, of course everybody measures the same time. Time is absolute. It doesn't matter how you're moving with respect to somebody else's clock. You'll see the same time as they will. But Einstein showed, and we sort of followed in his footsteps here, that put these two principles together, accept both of these accepted principles, and even though they seem to be in conflict, you get, if you accept them as true, you get the relativity of simultaneity. And from that, then, other results tumbled out. We talked about time dilation using the light clock example, again, coming from the invariance of the speed of light, so that a moving clock, an observer who observes a moving clock will observe it to tick more slowly than an identical clock that he or she has next to them. So time dilation. And from that, we also got the Lorentz factor gamma, the scaling factor for time dilation, really. And then from that, we get length contraction as we analyzed it further, that moving objects contract in the direction of motion to an observer who is observing the moving object. If you're riding along with the moving object, of course, everything in your frame of reference, everything is normal. It has its normal length because you're in its so-called rest frame. So it's rest length or proper length. So time dilation, the Lorentz factor gamma, length contraction. I won't write down the formulas here because you should know them by now. Of course, you can quickly remind yourself, review that. The invariant interval, I actually did write down this formula just to remind us. That also came out of an analysis of the light clock thought experiment, and we showed that for all observers, this combination of things from one event, two events in one frame versus another frame, c squared, t squared minus x squared will always be constant, and allowed us to do a few calculations with that. And then the phrase leading clocks lag, that we talked about the relativity of simultaneity, relativity of synchronization, but that if, as you observe clocks, two clocks go by and they're moving with respect to you, the leading clock will lag behind the trailing clock. And that was a key result we did both qualitatively and then later quantitatively once we had figured out the Lorentz transformation. And that was probably the most complicated analysis we did, mathematical analysis we did, the derivation there. But we got that such that we could transform between different inertial frames of reference very easily. If, again, Bob and Alice, if Bob measured a certain event in his frame of reference at a certain position and a certain time, if we knew that, and we knew then the velocity between his frame of reference and Alice's frame of reference, we could very easily figure out where would that event occur in space-time in Alice's frame of reference. So that was why the Lorentz transformation became handy to do things like that. And of course, we talked about space-time diagrams. We actually introduced them back here when we talked about relativity, but we made use of them in terms of Lorentz transformation, getting both frames of reference, as it were, onto the same plot, and did a few things with that. And then just looked at some of the famous implications of all this. Not that time dilation, length contraction aren't famous in and of themselves, but we considered the situation, can you have faster than light travel? We did one example where we had the spaceship going from San Francisco to St. Louis to New York, and showed that actually in that case it's an optical illusion that you get faster than light travel. The spaceship never goes faster than the speed of light, but it seems like to an observer in New York, say, that things are traveling faster than light. We looked at cause and effect situation where if you do have faster than light travel, you get a reversal of cause and effect, which is a strong argument against the possibility of faster than light travel, because we just don't see things like that happening. The universe doesn't work that way. There seems to be a definite chain of cause and effect. Although, of course, in quantum mechanics, it gets a little more complicated than that. But even in quantum mechanics, you don't have you don't have time running in reverse, essentially. At least in experimental situations. In theoretical situations, you can actually imagine time running in reverse, but that's a whole other topic which we didn't get into. So we definitely show the cause and effect that if you have faster than light travel, you can have something happening actually before its cause. And we did the example of the spaceship traveling away from a planet, and then the good guys traveling away, and the bad guys inventing a faster than light spaceship and traveling after them and actually destroying them. In the good guys' frame of reference, they get destroyed before the faster than light spaceship is even invented. So we say there's a contradiction there, and therefore can't happen. So more implications, of course, paradoxes. We talked about the pole in the barn paradox. We talked about the spaceships on a rope paradox. And, of course, we talked about the twin paradox. And then that led us on to, in the final week, talk a little bit about galactic travel. Is it possible, especially given the results of the twin paradox? In principle, it is, that you can travel to the center of the galaxy in a reasonable amount of time. If you're on the spaceship, though back on Earth, thousands of years will pass by. But then we ran into a problem when we considered the famous equation E equals mc squared, or the general form of it, E equals gamma mc squared. We discovered that the amount of energy to get up to the speeds needed, very close to the speed of light, to make galactic travel possible, even in just theory, is far more than we certainly know how to get at this point in time. And then finally, just a few words on general relativity, the equivalence principle between accelerating frames of reference and gravity, and therefore that led on to showing that actually in a gravitational field, time dilation occurs. We mentioned this is a factor in the GPS navigation system that has to be taken into account, that satellites are up here and we're down here, and therefore satellite clocks will actually run faster than clocks here if they're identical down on the surface of the Earth, so that has to be that time. It's not really a time delay, it's a time dilation factor. You have delay of speed of light signals moving from one to the other, but in addition to that, you have just simple time dilation. The clocks on the surface of the Earth will run more slowly than identical clocks on the satellite, so that has to be factored into the system. And the bending of light in a gravitational field as well. So a lot of things we covered. Amazing, actually, we can sort of get it all on one board, at least the key concepts here. So you can see where we've come. Hopefully that helps you get a big picture view, because, again, sometimes we get so caught up in the details we lose sight of where we've been and where we might be going with it. But I hope as we start off the course, one of the key quotes, we talked about not only the mystery of the marvelous structure of reality, we mentioned that several times now, but also Einstein's quote to the point that just the struggle to understand, and yes, it certainly is a struggle to understand a lot of these things, whether in the details or just even the big picture concepts as well, but that the struggle to understand can be an ennobling experience and even an enriching experience. I hope you found some of that as we've journeyed through this course together.